The topic that we're going to be doing today, oops, here we go, is section 5.2. So if you're wondering what today was about, Alison, it's about what's called the definite integral. Well, what do we mean when we say a definite integral? Well, it's just another way of saying it's just another way of saying find the exact value for the area under a curve. Which means that we cannot use any of the really boring T6, Simpson's 20, you know, those kind of techniques, right? They do not give you exact values. And they can give you very accurate estimates, but
I
they
want
do
you to
not give
train
us.
with me.
Say again, Matthew?
Yeah.
Is there a question there, Matthew? I'm not sure. You may be talking to someone else.
Oh, sorry. Sorry. No,
Okay.
I don't have a question.
Okay, I'll do that then. Just hit the space bar if you've got a question, because I'm kind of new to geometry. So we're going to have to find other ways to find exact areas under curves. That job is very difficult to do. So there's only a niche market. There are only certain situations where it can actually do it. The first one is not going to be any of the questions from 5.2, but I'm doing it as a complete, you know, just to be complete. We're going to show you can use a calculator. The second one is that we can use geometry to find the area under a curve, the exact area, provided the shape, right, the curve or straight line, whatever it's made from, is basically building blocks of rectangles, triangles, and parts of circles. As long as it's those things, right, we can find the exact area under the curve because we know the area of rectangles, triangles, and parts of circles. And then, based on my other class, we'll only get started on this and do maybe one, perhaps if we're lucky, 2 examples. We're going to do Riemann sums. And what Riemann sums is the algebraic way of finding the exact value for the area under a curve using sigma notation, using infinite sums. Very ugly, very messy, and a lot of people will tell you, if you talk to them, that Riemann sums were one of the worst things that you do in Calc 2, one of the hardest things. So don't be too shocked if you feel that, but they are doable. So let's start with the first one. That is not the first one, that will be my second situation. Let's suppose I would like to know the exact area under the curve from 1 to 3 of, I don't know, e to the x dx. Right. Well, calculator pretty much does everything for you. Got a question there? Yes, we were. We are. Someone says, I thought we were already doing Riemann sums. Yes, you have touched on them, so you have seen them. They're not totally new. So let's go over here and go y equals e to the power of, did I do that? Try it again. E to the power of, no, that shouldn't be that difficult to do. There we go. E to the power of x, done. Pick my window, which is 1 to 3. And then go to second calc. Option 7, which will give us the integral, the area under the curve. Something like that. Lower limit, 1. Upper limit was 3. It'll do some little animation-y thing. And the answer is about 17.36725. It has an exact value. Its exact value is actually e brackets e squared minus 1, but that's what that is as a decimal. Well, I guess we could just let calculators do all our thinking for us, but it's probably not a good idea. I would hate somebody to build a bridge by hitting buttons on a calculator and not knowing whether the answer was right or wrong, but only by trusting what they saw in front of them, because you can screw up, you can make mistakes. So let's go on to what 5.2 deals with. The first half of the questions are all about using geometry to find the exact area under a curve. So let's take this guy here. These lines I'm putting in here are not actually on the diagram, but they're kind of helpful, little guidelines essentially. Right. Suppose you're going to get the integral from 0 to 6 of this function. Since this function is basically just made up of straight lines of various kinds, I should be able to find its area. So, starting at 0, finishing at 6. And it's essentially this piece, right? I would probably break it into a triangle and a rectangle. Now, the area of this triangle is 1/2 the base, which is 6, times the height, which also is 6. And that's basically A. And then I'd add the rectangle. And that's a rectangle that's also, well, I guess it's a square, which is 6 times 6. So I get 18, add 36, and I get 54. So I know the exact area under this curve from 0 to 6. Well, suppose I wanted to get the integral from 6 to 9. Well, if you're doing 6 to 9, wouldn't it just basically be this little piece here? And that would be, what, a rectangle, 3 times 12. And that would be, what, 36. I could also get the integral from 0 to 9. Now, I want you to imagine that question A was this question and question B was this one. Is there any shortcut way I could get this area under the curve just using the previous two answers? I know this area is 54. I know this piece is 36. How would I get from there to there, that area?
You would add them?
Yeah. You would take the integral from 0 to 6. That's the area, right? And you take 6 to 9. And there's a little bit of simple algebra. Wouldn't these two combine to be the same as that guy? And so you add them. So you got a 54 and a 36. And that's 80, I believe. In this case, it's 90. Now, let's assume that was question C. Now, in question D, you might be asked to find the integral from 0 to 15. But I want to do this in the most efficient way possible. So that means I don't want to have to reinvent the wheel and calculate all the areas again from scratch. So couldn't I just use the fact that I already know the integral from 0 to 9? And then just add whatever 9 to 15 gets me. Does that make sense? That would be the least amount of work, right? You've already got some of the answer, just use the sum of the answer and add on the bit that's missing and you've got the whole answer. In this case, we already know the answer from here to here comes to 90. And then we're left with just one little triangle. So it's going to be a half, the base, which is 6, and the height, which is 12. So does that get 36? And that gets me 126. And bubble zoom some of these answers just so I can keep track of them all. There we go. Does that seem pretty intuitive? That if you want to find the exact area under a curve and it's just made up of straight lines, aren't you going to get rectangles, squares, and triangles of various pieces, add them all together, and boom, you got your answer? That seem reasonable? Nothing too weird looking? Right. Now, I'm going to break a rule that you've probably held for a long, long time. Here's a little piece of that picture. That piece there. And this is the x-axis. And we are going to find the integral from 15 to 21. And we know the exact area under the curve is this piece here, right? So far, so good. Now, this triangle is half the base, right? From there to there is 6. And the height, although it's not obvious if you count it, is 6. And you are going to think that the area is 18. So the area under the curve is 18. And the reason why you're going to think that is that for your entire math career, unless you've done calc before, you've always been told that areas are positive things. It is silly to talk about an area of -4 square feet, right? Areas are positive things, right? You've got that in your brain. So let me get it out of your brain. We talk in calculus about the area under a curve. And the reason why we use those extra words under the curve instead of just saying area is because there is a convention. And the convention is that if the curve is above the x-axis, you make positive positive areas. But when it's below the x-axis, you make negative areas. So I want you now to accept that as far as calculus is concerned, negative areas under curves exist. Right? Not areas, but areas under curves. So if the extra words help, that's good, right? So this is below the x-axis and its area is 18, so it's -18. So if I was going to find the integral from 0 to 21 of this function, it would be made up of 0 to 15 plus 15 to 21. And the piece from 0 to 15 is positive and is 126. But this little piece here is -18. So the result is 108. Are you okay with that concept that we talk about areas under curves and positive answers and negative answers happen? Right? If the curve is above the x-axis, your answer is positive. If the piece you're talking about is below the x-axis, then that will be a negative contribution to the area under a curve. Now, to finish this question, let's do 0 to 24. If I wanted to make the area under the curve from 0 to 24, if I wanted to make it with the least amount of work, wouldn't I use the answer I've already got and then add on the little piece at the end? Now, I know that the net effect of this is still a positive number, but not quite as big as it used to be. This tiny little piece at the end, is that going to be a positive contribution to the answer or a negative contribution?
Positive.
And isn't it just a baby triangle, a half 3 times 3? Agree? So you're going to have 1/2 3 times 3, which is 9 halves, which is a pain in the butt because that means everything has to become halves. So 216, 225 halves, and that would be your answer. So we have discovered that if you want to find the area under a curve, you can use you can use rectangles and triangles, but you also have to incorporate, is it above or is it below the x-axis? Because that's going to make a difference, right? Above, positive contribution. If the part of the curve is below, that's going to be a negative contribution. Now, here's a little side issue. Incorporating that above and below. Can you pretend I'm really good at drawing the sine function? And here is 0, and here is 2 pi. And I want to find the exact area under the curve from 0 to 2 pi. And if you need to know that, guy's pi. So I got this bit, and I got this bit. I know the answer to that, even although I don't know any of the individual pieces. What is the answer to that overall area under the curve?
0.
Right, correct. Why?
Because there's equal positive and negative area.
Agreed. The bit above is the exact same shape as the bit below the x-axis, right? This piece is positive. This piece is negative. I might not know what number that is, but don't I know that it's the same number that that is? So they're going to cancel each other out. So can you see in this case, the area under the curve is in fact 0. Now, we have a different name for what you would call area. We just stick the word net in front of it. So later on, a week or wherever we hit that, they'll say, what's the net area, right? In which case you would say that's 5 and that's 5, so the net area is 10, right? That kind of thing, right? But that's for a different time and a different place, so we won't worry about that. Before I forget, we're going to have another lesson tomorrow online. Same link as this one. I can tell just the way I'm coughing right now, I'm not going to be fixed by tomorrow, right? I'm an optimist at heart, so I'm hoping that after Wednesday I'll feel a lot better and maybe I'll be back by Thursday. But whenever I come back, thank God it'll happen soon, will just be the way the class should be run. So I really feel for the fact that I've kind of left you in the lurch where you're expecting to see me and have an on-ground experience, and what you're suffering is a less than satisfactory online experience, but hopefully you're still learning, right? Hopefully that's still working. Now, a couple of people have told me emails about what are we doing about this project one, because you're not here to, you know, like you said you would be on Monday to give me it. And what you're going to do there, if I haven't already told you, is hold on to it until I finally turn up. And when I finally turn up on campus, you give it to me then. And that way I get them all at the same time. So if you've already sent me a PDF version, I prefer that you just keep the paper version. If for some reason you threw it away after you sent me the PDF, then tell me and I'll print it out. So I've got a copy. Okay. Any questions about what we've just done before I move on? So pretty good, right? Would you agree it's a lot nicer than L6s and Simpsons 12s? They're just boring, right? These you can do, and conceptually, I think you can see what's going on a lot easier. So let's use geometry to find the exact area, right, under the curve of a straight line. Now, what I would do in a question like this is sketch the function. And that would be 1, it's 0 at least, then there's 1, then there's 2, then there's 3. When it's 1, you get 3, and when it's 3, you get 3. God, I should do better skills, shouldn't I? 3, 4, 5, 6, 7. Okay, we can still live with it. As badly drawn as I have done this, would you agree that the area under the curve is pretty obvious? And in this case, I think it would be natural to split it into a triangle, which I'll call A, and a rectangle, which I'll call B. And this guy is at 1,3, and this guy up here, although you can't see it, is a height of 7, right? So the answer to this guy is going to be the area of A plus the area of B. And A is a triangle, half of 2. And I believe from there to there then is only 4, right? And there to there is 3. Yeah, that makes sense. So it's a half. 2 times 4. And then a 2 by 3 for the bottom guy. So that's 4 plus 6. And pretty straightforward. Now, suppose, because I'm not going to do this in any great detail, but let's just suppose that it was a different straight line, and the straight line looks something like this. And you're being asked to find the integral from 0 to 4 of whatever that straight line was. Wouldn't you have to break the shape into 2 pieces, both of which are triangles? And let's just say, for argument's sake, that guy there ends up being 5, and this guy ends up being 15. The area under this curve is not 20, right? It's not 15 add 5, agreed? Won't the area under this curve be 15 take away 5, which is 10? Does that make sense? So you really do need to sketch the darn thing, because isn't there a good chance that some of it, or even all of it, might be below the x-axis, and therefore your answer will have negatives that you need to deal with. The next one is similar to one of the homework questions, and it's going to be the integral from -9 to 0 of 4 plus the square root of 81 take away x squared dx. Now, you might be very good in visualize curves, but sometimes just you can't visualize curves, right? You have to put them into Desmos and sketch them, right? Third set of notes. I don't know. Is that the third set of notes that someone put in the comment? The one before that, okay. Is that the third set of notes? I'm just fixing someone's issue. The one before that. That's the only guy I've got before that one, so I doubt it's that one. So is it this one? Hey, okay. So while that is happening, while he's getting a quick copy, let's take this fella and put it into Desmos so we can get an idea of what we're going to be finding the area under. So I'll get this set up for a few moments while the person gets his notes sorted out. Anybody any idea what that's going to look like before I actually put it into Desmos? Because I have it in front of me here. What do you think this bit's going to generate? Not sure. Something to do with a circle, actually. Okay, let's show you. Right, there you go. Now, do you see it's basically half a circle. It starts at -9, so I'm going to put -9 in my little diagram. The height that it begins at is at 4. And then it finishes at 9. So I'm now going to go back and show you my really bad rendition of that same picture, which is this guy. So I'm going to add an extra dotted line going this way and an extra dotted line going this way. And since you're only interested in -9 to 0, aren't we really only interested on this side? And the way I see it is that it's made up of 2 pieces. As badly drawn as I've done that, isn't that a quarter of a circle? And this bit here's a rectangle. So the integral from -9 to 0 of this function is going to be made up of quarter of a circle plus a rectangle. Now, since it's a quarter of the circle, I'm going to call it a quarter pi r squared. And b is going to be 9 units by 4. And everybody is above the x-axis, so everybody is positive. What is the radius of this circle? Because I need to know the radius to do pi r squared.
9.
9. Can you see it from a very badly drawn picture that from here to here and from here to here is a radius and they're both 9. So that's 81 because 9 squared is 81. So I'm going to get 81 quarters pi, add 36. And there is a temptation that you will try and turn that into 3.14 to get a single, number answer. Don't. We want exact values. And because of that, that is the answer. That is the exact value. So that's what you type into WebAssign, nothing else, right? And you're done. There we go. Just to prove to you that that is the case. You see it? Right. Here's what it, it's got a nice green check mark against it. Well, it takes us to our last step, the Riemann sums. Hopefully, the last time, you'll need to worry about them. Although I suspect we'll do some more tomorrow. Right, so let's talk about sigma notation before we even worry about Riemann sums. Because what Riemann sums are going to allow us to do is to find the exact value for the area under, theoretically anyway, any curve in the world. Theoretically. But in practice, It's so ugly and so complicated that we only do it with straight lines and quadratics, mostly. Right, so sigma notation looks like this. Sigma notation allows us to find an efficient, compact way to describe or represent a whole load of things being added. So for instance, if I did I equals 1 to n of 3, that would mean, well, let's put a number in here. Let's say 7. That's better. I equals 1 to 7. That would be 3 plus 3 plus 3 plus 3 plus 3. 1, 2, 3, 4, 5 plus 3 plus 3. There would be 7 terms here. And of course, the answer would be 21. On the other hand, if I did I equals 1 to 4 of, let's say, I squared, I is sometimes called the counting variable. So we have a variable that says start with I equals 1, plug it into this expression, and then add it to I equals 2, then add it to I equals 3. So what you get is 1 squared plus 2 squared plus 3 squared plus 4 squared, and you get whatever that is equal to, and you're good. But one of the powerful things about sigma notation, I could use it to represent that. Now, nobody here, I'm assuming that you're all sensible human beings, would want to write that down in full. Would you agree it would take 20 pieces of paper and you get bored, right? Because technically it would be 1 squared plus 2 squared plus 3 squared, and then dot, 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 and then you'd finish with what? In this case, 4,000 squared. So it's a very convenient way, isn't it, of representing a whole load of things being added together. In this case, the things happen to be squares. But you can take it even further than that. Oops. Somehow my sigmas joined together. You can go I equals 1 to infinity of I squared. Which means what? 1 squared plus 2 squared plus 3 squared forever. Hey, I have just in one small piece of notation described and written down a way of adding up an infinite number of things. That's a pretty versatile piece of notation, isn't it? That allows us to represent small things being added, lots of things being added, or infinite number of things being added. Now I'm going to give you some very useful special cases where someone has actually figured out what the answer looks like as a single value. So I believe it was Leibniz who did it. So here's the first one. I equals 1 to n of the number 1. That's a very simple one. It's 1 add 1 add 1, and you'd finish with the 1. And altogether, there would be n of these, n terms. So it shouldn't surprise you that that is equal to n. And that one is a pretty much, you could figure that out yourself. The next one is I equals 1 to n of I. So n is some arbitrary number that you're going to stop at, right? It could be n could be 20, it could be 20 million, right? Just n, right? It's a stopping point. So this would be what, 1 plus 2 plus 3, and you'd finish at n. So there would be altogether n terms again, but each one of them is different. And you might think, does that mean I have to add them all up? No. Leibniz figured out that it was equal to this guy. And there is a story that said Leibniz was, whatever he was, 12 years old, and he was at school. And the professor had to leave. And instead of just having the students do nothing, he gave the students essentially a job of adding up the first 100 numbers, right? 1 plus 2 plus 3, all the way to 100. And he gave it as a kind of, well, nobody's going to be able to do it in 5 minutes because that's all I'm going to be away for, but it'll keep them busy, right? That was the story. And he came back in 5 minutes or whatever, and Leibniz had already got the answer. Because Leibniz discovered this. So let's show you what it would look like. According to him, if you want to do I equals 1 to 100, right? Add up the first 100 numbers. 1 plus 2 all the way to 100. The key is n is 100. So it would be 100 times 100 over 1 over 2. And that's 50. So it's 5,050. And so he done it in, what, 30 seconds or less. Normally, we don't prove things to you, mostly because things are very difficult in mathematics to prove. You just have to, trust me, right? We never proved to you L'Hopital, did we? We never said, hey, L'Hopital, here's why it works, here's the proof of it. Isn't it more, hey, trust me, I'm a mathematician, it works, use it, right? Lots of things in your math life, you are just told that they work, right? And so let's prove this one to you, because we have some time, and I think it gives some insight into it. Let's call this thing A. Right, so the answer is A. Now, what do I know about it? Well, I know that A is 1 plus 2 plus 3 plus 4, and it finishes at n. Agreed? And then he said, if you add up a whole load of numbers, can you add them up front to back or back to front? So won't it be the same as adding them up in reverse? Would that make sense? That if you turned them back to front? Instead of going 1, 2, 3, 99, 100, couldn't you go 100, 99, 98, all the way down to 1? So if you add these together, you get 2A. Now, what happens if you add these two together? Well, you get n plus 1. And what happens if you add those two together? Oh, you get n plus 1. And the next two, you get n plus 1. In fact, don't you get n plus 1 every single time? Now, how many of these n plus 1s are there? There are n of them. So that makes A 1. So I've just proved to you that if you want to add up the first n whole numbers, the answer is n plus 1 over 2. And that was done by somebody who I believe was 12, 13 years old. Okay, he's an exceptional, one of those very gifted people, but kind of clever that he figured that out. So that's this one. Now, I'm not going to prove the next one to you. And can you just trust me? I'm a mathematician on the next one, but it is provable. I equals 1 to n of I squared. So that's basically 1 squared plus 2 squared plus 3 squared up to n squared. And there's going to be n terms. And that's what that is equal to. By the way, proving that one is, excuse me, is extremely difficult. So you're just going to trust me, right? Now, how are these guys going to help me to find the exact area under the curve? Well, I'm going to pick a function, and it's going to go from 0 to 3, and the function is going to be x squared dx. And I am going to use Rn, the right endpoints. So if I draw a little sketch of what that might look like. Right, can you imagine taking a shape, breaking it apart? Now, I'm going to do n strips. So it's not going to be R8 or R100. It's going to be n. It's going to be unknown number of strips, just n. So I need to know how wide each strip is. Well, we have a formula for that, which is that one. So those who've seen the earlier questions on the beginnings of Riemann sum will recognize that. In this case, it's 3, because that's A and that's B. Take away 0 over n, it's 3 over n. We then have another guy called xi. That xi would be, you know, that's x0, that's x1, that's x2, and all that good stuff. Xi is A plus I times delta x. So it's 0 plus I times that fella. So there's this guy. He's important. He's important. Excuse me. It is not a good idea to have an upper tract respiratory infection when you are asthmatic at the same time. It is just not a good combination, trust me. Right, so I would like to find Rn, right? Right hand sum. So if you think back, what does that look like? It's delta x, the value of the function, meaning the height 1, and the value of the function, the height 2, and the value of the function, height 3, right? And you keep going and you finish at the value of the function xn. And if you break it into its individual pieces, you get that guy would be the area of the first strip. That guy would be the area of the second strip. And this guy here would be the area of the nth strip. Now that lends itself to Riemann notation, right? Sigma notation. So Rn can be I equals 1 to n. I'm just going to switch the order a little bit. Put the f of xi first, delta x. And then I'm going to slowly but surely change each of the pieces. Instead of xi, it's going to be 3i over n. Instead of delta x, it's going to be 3 over n. Now the function was x squared. So f, think of this as being x, you get 3i over n squared times 3 over n. this becomes 9i squared over n squared, and this becomes 3 over n. So we now end up with I equals 1 to n of 27i squareds over n cubed. Now I'm going to do a little piece of trickery. Sigma notation says that if you have a calculation inside the sigma, as long as the pieces do not have an I in them, you can take them from here and put them outside. So we now have 27 over n cubed of that guy. And now this guy gets replaced by that. So we now have an n over 3, an n plus 1, and a 2n plus 1. That cancels with, my apologies, that's a 6. I'm not functioning well. That's a 6, not a 3. Right, that cancels with that cancels with that. What do I get? I get 2 in the bottom, so I get 2n squareds. That cancels, that's an n squared. 3 goes into that, I get that guy. And I get that guy. I'll FOIL this out and get 2n squared plus 3n plus 1. I'll get 18n squared plus 3n plus 1 over 2n squared. Now, n represents the number of strips that I used to find an estimate for that guy. So if I put 1,000,000 in here, this answer would be what you would get if you used 1,000,000 strips. So now we do something even sneakier. The exact value for this guy is what you would get if you used an infinite number of strips. That makes sense. If you could do as many strips as you wanted, couldn't you get the answer to the point where it would be the exact value? Make sense? Infinite number of strips, perfect answer. So we are now going to be finding the limit as n tends to infinity of 18n squared plus 3n plus 1 over 2n squared. Okay, this is going to get some cobwebs shaken up a little bit. How do you find the limit of a fraction like that? There are 2 different ways, both work. Did it in Calc 1. How do you find?
L'Hopital's rule.
Yeah, and the other one would be what, divide top and bottom by n squared, right? So L'Hopital it is. You're allowed to do L'Hopital because it's indeterminate form, which means it's 0 over 0, or in this case, infinity over infinity. So a little L to tell people you're doing L'Hopital. And if you differentiate the top, you get 36n plus 3. And if you differentiate the bottom, you get 4n. Now, if you plug in infinity, it's still infinity over infinity. So we just do, it's not uncommon. We do L'Hopital a second time. And 36 over 4. And the answer is 9. Wow. We have just found the exact area under the curve x squared from 0 to 3, and the answer is 9. Do you believe me?
Yep.
Right. Well, just to prove or to emphasize that it was right, let's go here. Y equals x squared. Zero to 3. second calc, number 7. Can you see how you can use this to check your homework? Lower limit 0, upper limit 3. We better see 9 at the end of this, or we spent 15 minutes doing nothing. Hey, are we good or are we good?